Welcome everybody to this March CBEC meeting. It's appropriately raining outside as we speak. I'm going to take a few minutes for everybody to get logged in, and then we will get started. Well, again, welcome everybody. My name is Nathan Sini. I'm an architect with Morrison Hirschfield. I'm the president of the Seattle Building Enclosure Council. Thanks for attending our meeting today. Changing the wrong slides. There we go. As you probably know, CBEC is a nonprofit organization that exists to further building science and knowledge and improve our building enclosures. We are powered by our board members who keep the machine running. Many hands make light work of getting all of these presentations together and off the ground. So thanks to all of our board members. Our next meetings are April 15th. It's an evening meeting. We haven't pinned it down exactly, but we're pretty sure we're going to have Simpson and Gumpertz present on some of their building enclosure research. And then in May, on the 20th, we have another midday meeting, and that is titled Amenity Spaces on Conventional Roofs. And it's going to be presented by Jeff Speart with 4EA, formerly JRS. We are reviewing our scholarship applications. We once again got a good batch, thanks to our education chair, Bill Thordarson. We will award that shortly. Our grant recipient from last fall is still reporting in on their progress. It looks like they're doing great work, and we will relaunch our grant applications this fall for another round. So if you have an idea of something you'd like to research that CBEC can help support, be ready to let us know. A few other local-ish building enclosure events. CSI Puget Sound is having a modern day concrete fireside chat with David Landry on the, that should be 3/23. And CSI Portland is also talking about concrete on 3/23, but later in the day, so you can still do both. The Boston Beck and Boston Architects Group is hosting their second WAGB Anna Symposium on Building Science this September. And their call for abstracts are currently open and due on April 16th. You can check out the Boston Beck or contact Susan Green to get more information about that. But I understand that the 2019 event was very well attended and informative, and recommend seeking it out. Next, we have James Olin with AVM Industries and Cascade Building Envelope Solutions, who is our sponsor for today's meeting. So James, if you'd like to take over.
Thanks, Nathan. Thanks for having us. We're excited to be members and part of the CBEC group, and just wanted to share a little bit about AVM before we get started. Some of you have probably heard from either myself or Asher previously, but Asher Rudian and myself are the two AVM contacts for the Pacific Northwest. We're both based here out of the Seattle market. You can see some contact information for each of us there. At AVM, we focus on below grade waterproofing and plaza deck waterproofing. So we offer a full line from HDPE fully bonded technology, bentonite swelling technology, and then hot rubber and polyurethane for plaza decks as well. So we've been out in the market, have had a number of jobs in both the Seattle and the Portland markets, and are looking forward to continuing to grow. If you have any questions or have any technical needs for below grade waterproofing or plaza decks, we'd be happy to help you and show you what we can do. Thank you, everybody.
Great, thanks, James. If anyone else is interested in sponsoring future meetings, please contact Joel Thornburg with the Amento Group. He's our sponsorship chair and can put you, can get you connected with another 5-minute quick pitch for future meetings. Today's topic is window sill pan flashings. Are liquid membranes suitable? And it is presented by Michael Wilkinson from RDH Building Science. Michael, please feel free to start sharing your screen and take it away.
Michael, you're muted.
Yeah, thanks. Sorry about that. Thank you, Nathan. I should be able to ideally screen share here. I think I'm still disabled though, Nathan.
Are you?
Of course,
I think
there's
I do not
technical
have
issues.
permission yet, to be honest.
All right, I'm just gonna make you the host.
Great, thanks. Okay. So I guess the topic for today is window sill pan flashings. Are liquid membranes suitable? Of course, they are used throughout industry in many jurisdictions throughout North America at this point and different construction markets. So I guess we have some amount of research we've done internally and for manufacturers where we sort of looked at some properties of these different materials and looked to sort of, I guess, better understand how these products perform in the field in sort of more real world situations. So this is the agenda for today or for the presentation. So what initially it'll be sort of what is the initial sort of history of industry sill flashing practices, what's historically been done. Obviously, if we went back several decades, we would have been installing building paper into the rough opening at the sill even. So there has been some developments over time. We'll talk about liquid membranes in this context. Obviously, there's many new innovative products and chemistries that are now present in the marketplace. However, some of these products obviously have a much shorter history than, say, peel and sticks in industry. We'll talk a little bit about some specific testing that we've done as internally, looking at long-term water ponding, sort of how water repellent are these products. Drying potential, because that's a huge benefit in theory of using a product that's more has a higher permeance than, say, sort of your typical rubberized asphalt peel and stick. And then also talk about gap bridging ability, which is really one of the key, most important elements of using this type of system. So we'll start with industry sill flashing practices. And again, if you have any questions as we're moving through the presentation, feel free to jump in. Obviously, there's a bit of a time limit, so hopefully most of the big questions will come at the end, but if something comes to mind or you'd like to discuss a certain item in a little bit more depth, feel free to jump in. So we do have a fairly long history of how we understand these types of products work. Obviously, different marketplaces will have different preferences, or different construction markets will have different preferences. Up in Vancouver, where it's also a rainy day, we tend to use peel and sticks with a little bit more frequency, whereas I know in your market in Seattle, there seems to be more of a tendency for using liquids. So there's obviously variability between markets. One thing is for certain though, when we talk about peel and sticks, they have some amount of history in this kind of an application as a sill membrane or a sill pan flashing. Now, the challenge with sometimes with self-adhered membranes is that it can get quite complex. There can be quite a lot of membrane origami in terms of the number of pieces, gussets that would need to be installed to adequately treat a window rough opening. So this is one of those challenges associated with using this membrane. It does involve a fair bit of work, of course, and detail-oriented work at that. can see here, cutting gussets out of the self-adhered membrane. That would need to be installed at the bottom corners. Then we're doing some additional membrane work. And all of this, of course, is just to adequately deal with the pinholes at the corners and adequately keep that sill condition dry and protect the moisture-sensitive materials beneath. So this is the reality. These kinds of details, obviously, they are more complex. They take a little bit more time to be done correctly. So this is one of the challenges with this product, even though, or this system, even though it's been used quite commonly in industry. However, of course, there are problems as well if it's overdone, if the design or the construction is overzealous with the use of impermeable self-adhered membranes or peel and sticks. We do have a good understanding of what happens, especially when we have moisture-sensitive materials behind. So this is not uncommon for many of the investigations we've done, and I'm sure it's familiar to many of you as well. Anyone who's sort of done lots of work in the Pacific Northwest has probably looked at some existing buildings and seen some failures related to a range of problems. One of them could be overuse of an impermeable product. One other sort of element that we do know as well, just based on experience as an industry, is that vapor permeable sheet and self-adhered products are typically not acceptable. This is not something that we would install at the sill of a rough opening in isolation or on a horizontal surface. This is pretty well understood. We've opened up enough buildings looking at that had building paper or sheathing membrane installed into the sill and seen some of the subsequent results. So this is actually a detailed, I think this is coming from building code, Canadian building code information historically, which is obviously not the best guidance in today's context, but this is where things were at maybe a few decades ago. And this is something we're all quite familiar with, just again, based on building investigations, that permeable products in this, sheet goods in this application are not necessarily a good idea. Perhaps there's some applications where you could get away with it, where you have lots of outward slope, but in most cases, this is considered to be, there's a good understanding of the risk of doing this. So this leads us to liquid membranes. So there is obviously some significant benefits to using liquid applied membranes, both as a air barrier WRB, as well as for potentially dealing with rough openings. It can be really cost effective. Definitely the speed of installation can be greatly improved versus a lot of that complicated self-adhered membrane work. And they can be very simple to install. Of course, there's some caveats on that front. They can be used in isolation. We could combine them with self-adhered membranes at the sill if we wanted to use a peel and stick. They're quite versatile in general. So this is sort of there's many typical products that are available in industry now for detailing rough openings. They may come in sausages, they may come in pails. The end result, though, of course, is something that you would install around the rough opening. It sort of simplifies this detailing. Again, the corner detailing, a lot of that complexity associated with peel and sticks or self-adhered membranes is removed. So, I mean, the installation is pretty simple. You would obviously do so maybe there's some priming work, just the substrate, and some treatment of gaps and joints between the sheathing and the framing. It could be wood and say plywood or OSB sheathing. It could be steel framing with, say, gypsum sheathing. Really, there's many different combinations. But once that treatment is done, it's relatively straightforward to apply the liquid. And we end up in a situation where we have, in theory, a fairly well detailed and treated sill, and obviously jams in head of the rough opening. This can really speed up the installation versus what you could imagine would be several different pieces of membrane to adequately treat this rough opening. And then, of course, sealing at the back. In this case, we're sealing, we have window clips securing the window, and we're doing a perimeter interior seal and making sure we're bedding our clips. But liquid membranes, of course, do have challenges as well. They tend to be a little bit more susceptible to mechanical damage versus some of the, at least the thicker self-adhered membrane products. This is sort of a known challenge. Also, compatibility and adhesion with adjacent materials can also be a challenge, whether that be certain sealants being able to adhere to these types of liquid products of it, depending on chemistry and the manufacturer. But there's a whole range of tines that are always necessary in any building, and understanding that is obviously quite important and can be a challenge. So obviously this is something that's pretty well understood within the industry. Now, the question really is, so are these products suitable to Sill? They obviously have somewhat of a history of use now, and more or less successful use in industry at this point. Obviously, if you can address a lot of the detailing challenges, make sure it's protected, make sure that all the gaps are treated adequately, then perhaps it's in good shape. There are a range of industry standards that would be on any data sheet that would provide information on a range of properties. These ones are often AMA 711, 714. 714 is directly referring to liquid membranes and would have a range of different tests associated with it, whereas 711 would be more associated with self-adhered products. But at the end of the day, though, this will cover a whole range of different properties, and there's a good understanding of several sort of, I guess, properties that would be necessary to understand effectively if this were being installed in the field. So nail sealability, UV and temperature stability, adhesion after maybe being installed or installed on different types of substrates, whether they're cold substrates, whether they're wet substrates. This is relatively well captured within existing standards, largely ASTM standards. But there are some performance metrics that at this stage, at least, are not covered satisfactorily. They're not really representative, or these existing standards do not cover necessarily some of the other elements that would be nice to know or would be important to know about using these products. What we have found is that some liquid products that have very similar vapor permeances, they tend to have, or they often have different, or quite significantly different, water absorption rates. So we can't necessarily rely on vapor permeance, maybe from ASTM E96, say the wet cut method, to adequately understand how this will perform if there's, say, a water head. Also, there's obviously many challenges on any construction site in terms of understanding how that product deals with gaps. How does it deal with the gaps when it's installed? How does it deal with the gaps in service? Maybe as we're talking about shrinkage and expansion of wood materials when they're exposed to moisture. How does it deal with those kinds of considerations? So we do have a good understanding of a lot of the properties of these products, and many of the lab tests do cover these properties quite effectively. But there are several things that, at least in our opinion, would be good to explore further. Water ponding resistance is one, drying potential is another. Flexibility and the general ability to manage joints and gaps in framing, between framing and sheathing and other elements. Compatibility and adhesion with other materials is also a very important one. How does this liquid product bond to different substrates? How do we bond, say, different sealants and membranes to this product? Understanding those things are obviously important. How does the curing process, because we're dealing with a liquid, it obviously is going to tend to be impacted by different environmental conditions. Is it easy to install and workable? And then what's sort of the long-term performance of this kind of a product? In most cases, you would expect the product to be protected after the building's closed in, but sometimes maybe a building is going to have the membrane exposed for a significant amount of time. What actually happens in that case? So some of our investigations, we looked at 3 of these properties. We didn't get into everything else, and we found these ones to be some of the most interesting and important properties to evaluate in more detail, given the sort of some of the more the existing standards don't adequately cover these properties. First one is long-term water ponding testing. So what we did, and this was actually several years ago now at this point, we basically devised a test where we constructed a series of window rough openings, or the bottom of window rough openings. Each one of these mock-ups included a a wood sill. It had OSB sheathing and plywood sheathing on opposite ends of the mock-up. Basically, the premise was, at this point, we have a fairly good understanding as an industry in how permeable self-adhered membranes work in a sill application. I mean, there's quite a lot of history on this front. It's a good understanding of how they perform. And we also all know where, or have a good idea of how permeable sheet goods like house wrap or sheathing membranes perform, just based on experience, investigations, and whatnot. So at this point, we had sort of two ranges. We know that one is completely not suitable, and we know that one works quite well and has a long history of use in that kind of application, as long as it's used within reason. But we did not have any at this point, and maybe this has changed in the past couple of years, but there really wasn't too much comparative data that suggests how water permeable, water repellent liquids performed in this kind of an application. In particular at the sill, where there is potential for having some amount of water head at different points, whether it be from a leak or other reason. So the idea was to compare how these liquid membranes performed versus our two control membranes, our self-adhered impermeable membrane, sort of rubberized asphalt peel and stick, versus a self-adhered permeable product, a product that would have maybe a perm up around 30 or more, 30 perms or more. So a little bit more information on how we set this up. So we constructed our sill mock-ups with 2x6 framing. Of course, we have our OSB and plywood sheathing. We applied the membrane, allowed it a sufficient period of time to cure. We installed moisture content pins at several locations in both the sheathing and within the framing, just to understand the different moisture uptake properties of these different types of wood materials. And then we closed in each one of these mock-ups with plexiglass and sealed it in place, basically to make it dam, so we could contain a certain amount of water head. I should say at this point, so what we did in this case was, this would be more of a stress test. Of course, in most situations, you would not have this level of water head, but we installed 2 inches, or we had 2 inches of water head. It equates to a reasonably high hydrostatic pressure relative to what you would expect in service conditions. But we did this as a stress test, just to sort of see how the performance of these products would compare. This would accelerate that process, because we're only going to be monitoring over a period of 6 weeks, or we only monitor over a period of 6 weeks, accelerate that process of understanding water transmission through these various membrane products. So this is the first set of results. What we did in this case, we have a range of different types of membranes at the base. On the x-axis here, we have some Stpe-based products, some silicone-based products, some water-based acrylic or water-based polymer type products, elastomeric polymers, and then we have our controls, our vapor permeable self-adhered membrane and our vapor impermeable self-adhered membrane. And you can see, looking at this graph that shows our data here, that some things are more or less as expected. Again, this is a bit of a stress test, so it was 2 inches of water head, which is a fair bit, and definitely not something you would ever expect at the sill of a window rough opening in service. But nonetheless, you can see our self-adhered permeable membrane fails fairly early. And then if we look down over at this end, our impermeable peel and stick performs more or less as expected. And then we have sort of a range. Our liquid products tend to fall within a range between those two conditions. So looking at the 2x framing, there's not any significantly dramatic trends. I mean, a moisture content of 20%, we consider that to sort of be the safe line. Maybe above there's a risk of mold and fungal growth. Now, if we start looking at plywood, though, in particular that connection where we're detailing our liquid membrane over from the dimensional lumber over onto the sheathing, things start to become a little bit more dramatic. You can see here in our testing, some of the trends that looked fairly minor when we looked at dimensional lumber start to look a little bit more dramatic when we look at plywood. The permeable self-adhered membrane fails relatively quickly, and the impermeable self-adhered membrane obviously is quite durable in this condition. It is a waterproofing membrane. So looking at this data, it appeared that some of these liquids that perform more similarly to permeable self-adhered membrane probably would not be, or would be a higher risk product to use in the Sill application. Again, this is a stress test. Then there's some products that maybe would fall within a range where there may be moderate risk, and then you have some products that tend to trend more in line with impermeable peel and stick and would be more sort of more similar in performance to those kinds of products. OSB, here's another similar trend. Again, we're dealing with the edge grain of the sheathing. This can be quite a bit more significant in terms of water transmission through the membrane into the material. And again, a lot of the same trends exist. They look a little bit more severe in this particular. In our monitoring looks a little bit more severe in this particular case. But with that being said, it's a lot of the same trends we observe with the plywood sheathing. So again, some of these liquids seem to perform quite similarly to a permeable self-adhered membrane. Some are in sort of this middle range, and then finally some sort of trend more along the lines of an impermeable self-adhered membrane. So obviously looking at the samples as well, obviously we're monitoring the moisture content, but that also often indicated things that you could visually observe. So in this case, due to water transmission at this OSB edge grain and swelling, you can see that the membrane eventually failed, it sheared, and then more water got in, and obviously this specimen failed quite dramatically. Other liquid membrane products sometimes absorbed water. There was a certain amount of absorption that occurred, and the membrane became discolored under, again, this high amount of hydrostatic pressure. Some of the samples actually experienced mold after about 30 days, again, indicating that the moisture content was sufficiently high and the OSB was sufficiently wetted to create an excellent environment for mold or fungal growth. You can see it there. This is really what was happening and why we understand the edge grain to be a much greater challenge. Again, is you have water transmission through the membrane if it's water repellent, but maybe on the higher end of water or the lower end of water repellency, it can cause the edge grain of the OSB or the plywood to swell, and that sort of, it's a positive feedback loop that further increases the risk with some of these, or at least in some of these cases. And there you can see the swelling edge grain, and of course that's occurring because of water transmission through the membrane as the edge grain absorbs water. What about thin membranes and tapes? Obviously these are liquid products. In this case, we have our same controls. We have an impermeable self-adhered membrane and a permeable self-adhered membrane. But maybe thin membranes and tapes, this is something that often we sometimes see as well in windowsill applications. And in this case, some of them may be okay, some of them may not. So it's kind of an interesting trend on this front. What does this all lead us to? Well, really it comes back to the importance of subsill drainage. Obviously, the amount of waterhead that we tested in this case was 2 inches. It was much more than you would really realistically expect in real world conditions. If things are done correctly, of course, limiting the amount of water over any of these water repellent semi-permeable liquid applied products is very important, regardless of how well they perform in this water ponding test. So this sort of drove home the importance of having good subsill drainage, of having some way of weeping any water that finds itself sitting on that horizontal surface. Adding slope can sometimes be beneficial as well, of course. And there's a whole range of different solutions for that, whether using all different shimming systems, whether notching the flange on, say, a vinyl flanged window, but in one way or another providing subsill drainage. And this really drove home the value of that. We also looked at the drying potential of some of these products. How do they perform I mean, the fact that they are semi-permeable in many cases, does that provide a benefit? We know that in our Pacific Northwest climate, wood is wetted consistently during the construction process, particularly when we're building throughout the winter, and there's really not much ability to dry during that period in many cases. And then if we slap a impermeable self-adhered membrane over and we imagine there's a whole bunch of other framing, other elements that are on the other side, that can be problematic in some cases. So this is another property that would be we found quite interesting to look into in a bit more detail, just given the fact that maybe this is a valuable property that some of these liquid products have relative to other types of systems. So in this case, we constructed a mock-up that had plywood and it had dimensional lumber. We installed moisture content pins once again. You can see where these would be located within our mock-ups. And then we had a whole range of different samples, our membrane products installed. We had a self-adhered impermeable membrane installed as a control. We had a permeable self-adhered membrane as another control, again, our ranges. And then we looked at some different membrane products, liquid membrane products, to see whether there was a measurable benefit. It's important to note at this stage that we did well, first of all, we sealed the edges of our mock-ups with an impermeable peel and stick to limit lateral drying. And then we also left the backside of these mock-ups open so that they could dry, and placed them under a hut on a roof where they were exposed to exterior conditions, our typical Pacific Northwest winters where it's very high relative humidity. So they did not get UV exposure and were not able to sort of rely on solar drying. So there's potential perhaps for enhanced drying. In this case, we assumed that there was maybe potential for drying to the interior as well, but of course this isn't always the case. And then we compared these liquid membranes against the control membranes that we're quite familiar with their performance. So looking at the dimensional lumber, sort of looking at the sill, the 2x sill framing, this is the trend we saw. Again, if we look at the x-axis, we see that we have our permeable self-adhered membrane is the lowest, and our impermeable self-adhered membrane is more towards the top. Of course, it isn't the top in this case, but really what this is showing is that in this case, there really wasn't too much of a benefit with using different liquids as opposed to self-adhered membrane products. Plywood is a slightly different situation. In this case, we did see a bit of a difference between one of our controls and the other membrane products. In this case, again, so we started off with our wetted mock-ups, placed them on the roof under a hut so they could not be exposed to solar drying. And we observed the drying rates. In this case, it does look like, again, it wasn't too much benefit with liquids, but there was a slight benefit with using a permeable self-adhered membrane, relatively minor. Now, the reality is this mock-up test isn't necessarily always reflective of real-world situations, because in many situations we have stud framing that really is going to limit drying in perhaps at the jambs, or we'll have headers. And we'll have situations where there really isn't a huge amount of ability for interior drying due to buildup of framing. In some cases, if we have steel framing and we're using plywood liners, that's sort of an extreme condition, but this does happen quite often. And what we did look at, actually, in some case, we looked at whether there was a benefit. In this case, we're not looking at liquid membranes in particular, but we're looking at a sort of a steel stud framed assembly with a plywood liner. And in this case, we can see that we're looking at a impermeable and a semi-permeable product. These aren't liquids, though, in this case, but we can see that there can be a benefit to actually having a semi-permeable product, or a product that at least allows for some amount of outward drying relative to a standard rubberized asphalt adhesive peel and stick. So what's the answer to this? Well, in this case, it does look like in some cases, especially when we consider some of the challenges with interior drying related to additional framing members, and in particular, when we're dealing with steel framing and wood materials, there can potentially be a benefit for some of these products. Now, gap bridging ability is one of the most important elements related to using liquid applied products. Obviously, there's gaps in sheathing. There's going to be gaps between the framing, and the sill. And this is obviously quite a significant challenge for liquid products, which is why most of the manufacturers and many of the manufacturers have some kind of treatment regimen to deal with these gaps. So in this case, we had some mock-ups of the membranes constructed. We had fiberglass face gypsum, and then we had that had its factory edge in place. And then we had our specimens basically installed across a range of different gaps. And we allowed them to cure over a period of 72 hours. So we installed them across a gap, which again is not uncommon. A lot of the time, there are liquid materials where the contractor perhaps does not install some kind of a joint treatment or a reinforcing system across some of those gaps. And this was really, the intent of this was to illustrate what some of the challenges are with that kind of an approach. So we looked at 1/4 inch, 1/8 of an inch, and 16 inch gaps. And these are the results after 72 hours. We looked at a range of different liquid products with different chemistries, different thicknesses. And what we saw was that that many of the products, of course, did not perform or were not able to cure without having some kind of a failure across any size of gap. Some of the thicker applied membranes tended to have perhaps an ability to manage some of that sort of on our typical site gapping that you would be experienced. But in general, the trend is that this is that if obviously you do not have some kind of reinforcement or some kind of joint treatment, it can be a big challenge with using liquids. And again, thickness is really one of the big takeaways here. Thickness tended to improve the ability to manage these kinds of conditions. This is a couple examples of failure. You can see that our membrane here has sheared on the left. The one on the right is sagging. So I mean, issues or situations like this when we observe them would be sort of counted as a failure. We also looked at dynamic gap bridging. Of course, there is the potential for wood materials to shrink and expand, whether it be during the construction process, and of course, there's going to be some amount of movement also during the drying process once the building is closed in. And what we saw with this, or what we did with this, is we had an apparatus. We allowed our specimens to cure over the manufacturer's recommended period. And then we essentially opened and closed a gap to, I guess, larger and larger spacings. And usually each gap was closed over a period of about 30 minutes and opened over a period of 30 minutes. Just to sort of see what the potential impact of that is again. And once again, some of the similar trends were observed where really thickness is one of the primary things that needs to be managed. But most of all, really comes down to joint treatment and reinforcement. And again, this is something that many of the manufacturers, I would say most of the manufacturers recommend, but it is something that is absolutely necessary for using these products in the field to deal with the irregularities in the substrate. And there's different ways of doing it. Of course, there's some products that can be more applied similar to a sealant. There's products you can rely on a sheet or a self-adhered membrane product to span gaps. But at the end of the day, our research and certainly experience in the field has definitely indicated that having some form of reinforcement is absolutely critical. And then finally, in terms of conclusions, what can we draw from some of these tests that we've completed? What are some of the takeaways? Well, first of all, a lot of the results from this testing certainly confirm common industry assumptions and understandings. I think as an industry, we're pretty aware that plywood and OSB are going to be more susceptible to moisture uptake and decay than dimensional lumber. Where the self-adhered membranes performed more or less as expected, the impermeable and the permeable self-adhered product. Some liquids are certainly more water repellent than others. But regardless of liquid product, the subsill drainage is going to be one of those things that is very, very important. And So good design is incredibly important for any one of these products. Thicker membranes tended to have better gap bridging capabilities. This again drives home that point about reinforcing gaps and cracks in some way or another, and the value in doing that. In terms of drying benefit, that early testing, especially if we had an ability to have interior drying, did not exhibit significant benefit over the impermeable self-adhered membrane products that were tested. That being said, in some situations where there is additional framing that potentially limits interior drying, some of these trends may look a little bit more promising. Finally, what we would recommend going forward, or one of the sort of things moving forward that would be beneficial for our industry, would be a better understanding of how these liquids are actually performing in the field. So monitoring the field would be beneficial. Absolutely. Number of properties, moisture content, drying rate. And from this research we've completed as well, we see it as sort of being hopefully a driver for the development of new ASTM or AMA test standards that better reflect some of these other properties that may not be adequately covered at this time, in particular when we're installing liquids in flashing applications on horizontal surfaces. And that is it. So at this stage, is there any questions, items that you'd like to get into in a little more detail?
We do have a few questions.
Sure, Nathan.
Let's see. So Lauren Branford asked, how does gypsum sheathing affect these findings in terms of wetted sheathing affected framing? It looked like
How does gypsum sheathing perform?
Yeah.
I think for most of our water ponding testing, we've looked more at wood materials. So we don't have great data on that, unfortunately. We do know from field experience, of course, priming the edge of the gypsum is very important in terms of installing liquids and having a successful installation. But that would be a great thing to look at further in the future.
Okay. And then Carl asks, the original Sill design for the BEI Prosoco product had a flap of WRB as transition. This was embedded in the Sill, which would further protect the edge grain of the OSB. Is that?
We're talking about the Vapro Shield system where there's a sheet good beneath the liquid. Is that correct?
I think he was referring to R-Guard.
R-Guard, yeah. I mean, if you have a sheet good, we're talking about a permeable sheet good, then I suppose that's going to help with reinforcement, which is a big benefit. So it helps a lot the gap bridging ability. Again, though, if that product's permeable, and we did look at products that did require some of the manufacturers require systems that have a sheet good and then they have a liquid on top. And we did look at those as well, and those didn't necessarily perform in the water ponding test any better than if that sheet good was not present. Okay.
But they did perform better in the movement.
Yes, absolutely. I mean, yeah, it's reinforcing that transition.
And those the dynamic bridging tests were all prepared kind of per manufacturer, or did you test with and without reinforcement?
Yeah. So they would have, I guess, they would have been prepared without reinforcement in almost all cases. We did look at one product where we had the reinforcement per the typical install and one without. But yeah, the intent of that testing, certainly a lot of the manufacturers have good details and good instruction on treating gaps in joints. But we have also seen a lot of cases where that hasn't been done. So it's more looking at what can happen in that regard if we don't install those materials.
Okay. Lee asks, is it a reasonable interpretation of these results to say that silicone-based liquids tend to be relatively safe?
I would say further research would be valid, but I guess based on some of this, I mean, again, it's a stress test. It does look like some of the chemistries do sort of fall within different ranges, and the silicones tended to perform much more similarly to the impermeable self-adhered membranes, partly due to thickness, partly perhaps a little bit to chemistry, but thickness was one of the big factors there as well. I think a lot of the silicone liquid products that are available, they tended to have a thicker installation thickness than many of the other membranes.
In that initial stress test, there were, when you decided that something had failed, did it just drain all of the water out? Was that the stopping point of those graphs?
Yeah, I think in some of the initial graphs, you would have noticed that a couple of materials were sort of stopped. They didn't continue for the full 6 weeks. And those ones would have terminated because of a significant failure where essentially the water was draining. There was a problem, the membrane failed, and the test was not able to continue for those specimens.
Okay. Samuel says, so assuming impermeable self-adhered membranes are the better option on a sill, if a manufactured system calls for a liquid applied membrane detail at the sill, is it important to adjust the manufacturer's system to include for self-adhered membrane?
So this is an interesting point. I mean, I think liquid membrane systems can work adequately in many circumstances. Obviously, I would characterize them as having, some would have higher risk, some would have lower risk, depending on thickness, chemistry to a degree as well. The key thing, I mean, I guess the way I would characterize it is that yes, you can certainly combine those liquid systems with impermeable peel and sticks. I don't know if I would recommend necessarily going completely against what the manufacturer is saying, but if they were in agreement with that approach, then that would be more than adequate, I'm sure. I suppose the biggest factor here is really having good design of the sill as well. I mean, these systems, some of the systems are less water repellent perhaps than others, and but I mean, you can imagine if there's not any real waterhead that develops, then that really isn't too much of a problem.
Sure. Joel asks, are there any drawbacks to using silicone products in relationship to adhesion of other products?
Ooh, good question. I suppose there's probably a range of things we can get into. I suppose adhesion to adjacent materials can sometimes be a challenge with silicones. So that would be, I mean, I guess often when you're using one system, but this isn't just the case with silicones. There's you're tied into often using a manufacturer's system or using products that have known compatibility with those systems, and that isn't always the case. So maybe if you're using a silicone system, you are tied in with using, say, silicone sealants, whereas some Stpes, maybe some silicone sealants won't bond super well to them in some cases. So maybe in those cases you would require maybe an STPU or some kind of a hybrid product. So there's a bit of, compatibility sometimes can be an issue in bonding with silicone. I guess that would be one of the challenges with silicones. But again, it comes down to design to a degree in terms of ensuring that all adjacent materials will work adequately.
All right. Dan asks, on the drying potential tests, why were the test samples not framed out, insulated, and sheathed and clad below the sill plane to more accurately represent real-world conditions?
It's a very, very good question. I think initially we wanted to see what the impact of interior drying is, because at the sill, in some cases, you may not have too much interruption to interior drying. But we did also complete some testing with other products where we did fully sort of block out the condition behind to limit drying. And we also looked at steel liners, like that one graph where we're looking at some tape products. And in those cases, some of those trends actually did appear to be a little bit more beneficial in terms of improved drying potential over your standard peel and stick.
Okay. You said that the drying test took place under a roof, but exposed to the exterior. What were the conditions for the water sill test?
Yeah, so it would have been, the conditions for the drying potential test would have been done outside, actually on the roof of our old office. We had a sort of a shed roof built over top to ensure that it wasn't exposed directly to either rain or to sunlight, or I guess solar drying. So that was more or less the situation on that front. I'm sorry, there was a second part of that question, wasn't there, Nathan?
The second part was what in the water test, the first test, what were the conditions? Those looked like they were interior.
Yeah. So the ponding test was completed inside. It was more of a lab test. We did actually look at how some of those samples performed when we put them out in the field as well to see how they perform with wetting and drying. But it's a little bit more difficult to control circumstances in those cases. And you can imagine if you have a rain event, then our mock-ups fill up with water, and it's a little bit more difficult to control. So I mean, I guess this kind of harkens back to that point about actually getting monitoring equipment in some actual real world applications and sort of seeing some of those wetting and drying trends, maybe from installation of the liquid product all the way through till closing in the building and maybe in service for a year or two. And that would be, I think, pretty useful information to have.
Okay. Daniel asks, based on your testing and field observations, would you be inclined to recommend that sills that are to be coated with a permeable liquid applied membrane be reinforced with some sort of fabric?
Based on what we've seen, yes. I mean, again, some systems have other reinforcement materials they use or joint treatments, but I think in all cases, we would recommend using some form of reinforcement, whether it's a sheet good, whether it's peelant, like some kind of a self-adhered membrane that works with that manufacturer's system, and certainly joint filler, mesh, some kind of reinforcement. And again, most of the manufacturers do have some kind of a system that is reinforced.
Okay. Joel asked, did any of your testing of the coatings ever indicate moisture readings above 20% taking place when the sill was allowed to drain?
So that's a good point. And again, it comes back to this being more of a stress test. Yeah. We didn't sort of allow for real world conditions where in reality, there's going to be sort of a cycle of potentially wetting and drying, maybe if there's a leak. Unless again, you have poor subsoil drainage and there's water contained in that pocket that's not able to leave. Yeah, unfortunately, we didn't really look at that condition in any huge amount of time.
Okay. And the mock-ups used wood framing. Do you expect any difference in results if steel framing is used or on concrete walls?
Oh, so I suppose with steel framing and say gypsum sheathing, still going to have many of the same issues with gap bridging and managing those kinds of conditions. So that's still going to be a challenge, whereas perhaps concrete would not have that same challenge. I suppose the gypsum is obviously can be a little bit sensitive to moisture, but is probably going to be more resilient than the edge grain of plywood or OSB. So there's a bit of a change there, likely. One big thing though is I suppose if you are installing plywood liners in your steel stud framing, that can be a bit of a challenge, in particular for impermeable products. So maybe in those kinds of conditions, there is some benefit maybe to using the liquid if it can enhance drying in those I guess where interior drying is heavily limited, or I guess steel is essentially impermeable, so almost 100% limited.
All right. A different Joel asks, do you consider Stpe products to be sufficient on rough openings without the use of fabric or mesh if the Stpe product has reinforcing fibers?
Ooh, it's a good question. I would say in general, our experience is sort of has been that actually doing the pre-joint treatment some way or another is beneficial rather than relying on sort of integral reinforcing in the liquid. I mean, thickness can help to a degree of the liquid. That's something that many of the manufacturers can potentially look at and improve some of the properties. But I think in general, we've found that certainly completing that joint treatment regimen before installing the liquid rather than combining that process, we find that to be maybe a better approach.
Okay. I think those are all the questions from the Q&A. Do you guys have, are you guys working on any next phase of this project? Do you have another thing you're going to test?
At this point, we are not, but I think there's, it would be excellent, like I said, to get some field monitoring equipment and maybe have that installed in a wood frame, maybe a mid-rise building, and actually get some better data on that front. I think, and even if we sort of simulated leaks or things like that, where water is essentially running through and being trapped in that space, just to get a better idea of how this would work in the real world. I think, again, our ponding testing in particular is It's very much based on sort of more of a stress test to sort of see, to exacerbate that that process. So I think that would be nice to do, but at this point we don't have any new research on the books for this. Hopefully we will, or others will.
Maybe you guys can apply for the CBEC research grant.
Perhaps.
Yeah, I think the stress tests are certainly a valuable information, even if they don't necessarily have, real world equivalents. So I appreciate you guys, taking that step and kind of pushing the boundaries there. Do we have any other questions from the audience, the attendees? Had a great showing today. We had 86 people at the high point, I believe.
Thank you all.
All right, not seeing any additional questions. I'm just going to wrap up the meeting. Thanks everyone for attending. We have a great time presenting these, and we are looking forward to seeing you all again in April. And we noted that I advertised our May meeting. CBEC has officially decided not to host our May symposium in the coming year, due to the pandemic and other factors. But we are working with Portland to put together either a joint event or a future symposiums. We're looking forward to hosting you all in person again sometime soon. So thank you, everyone. Take care, and we'll see you again next month.
Thanks, Nathan.
Thank you, Michael.